Hello everyone, I just wanted to go through the concepts that we were going to cover today had I been in class and give you the opportunity to practice some Regents level problems related to those concepts. So for starters, we're going to back up for just 1 second and give a recap of plate boundaries. There's 3 that we're responsible for, and I think you probably are aware of them by now. Number 1 is a transform plate boundary. So in this case here, we have plates that are sliding past one another. Now because there is nothing subducting, and just to refresh, subducting means to go beneath another plate, which is happening down here at this convergent plate boundary. Because there's nothing subducting at a transform plate boundary, we don't have any volcanoes, which is nice, but we have plenty of earthquakes, and they're actually considered shallow earthquakes. Shallow earthquakes, I know it sounds like shallow versus a deep earthquake. A deep one should be able to do more damage, but remember, we build all our stuff up on the surface, so shallow earthquakes happen close to the surface, and they tend to cause more damage to people and the things that people build, the things that people cherish. So transform plate boundaries, sliding, yes. Earthquakes, yes. Volcanoes, no. Now a convergent plate boundary, we get a much wider array of activity, a much wider array of violence, really. But if you think about what's actually happening here, I mean, it's kind of fascinating to think about plates moving around, but you're talking about huge chunks of a planet are smashing into each other. And in a lot of cases pushing underneath each other, subducting. When you get that kind of motion with like miles and miles of rock, you're going to get a fair amount of activity, a fair amount of violence. So earthquakes and volcanoes are associated with convergent plate boundaries. Typically what happens is well, we're going to give you all 3 types. We have oceanic, continental, we have oceanic, and then you have continental, continental. Now there's some behavior differences between these 3, so I'm just going to real quick point them out to you. This is the one that you're going to find most common on the Regents. Oceanic crust is made out of basalt. It's a mafic rock. You guys know that from igneous rocks. Continental is made out of granite. It's felsic. So oceanic is more dense than continental, so the oceanic is going to be the one doing the subducting. In other words, oceanic is going to dive under the continental. The continental will stay on top. When it comes to oceanic, interestingly, the younger oceanic crust usually stays on top. So the older oceanic crust will usually dive beneath the younger oceanic crust. And then continental, nobody dives underneath anyone. They just like push each other up, and they get taller and taller and taller. And so there's some behavior differences between all 3 of these convergent plate boundaries. So let's get down to some of the basic facts that we need to remember here. So this plate here, look at the Juan de Fuca plate and the North American plate. This is the subducting plate. It means that this plate here, in this case it was the Juan de Fuca plate, is subducting or going underneath of the continental plate. Subducting is a word you just have to know. It's not on the reference table. It's not a word you probably know from your other life, your outside life. You weren't like, walking the door after school. Hey, hon, what were you doing today? Says your mom. Oh, nothing, just hanging out with friends, doing some subducting. It's not a word, it's a new word, it's a vocab word, but it's an important one, and it means to go underneath of another plate. The Regents will just use it plain as anything. They just expect you to know what it is. So to subduct means to dive underneath of another plate. Now once it gets down there, what the material that made this plate in the first place was already less dense than the mantle, so you're going to get some melting, and that's where we're going to get some volcanoes. Now this is not just volcanoes. When you shove this plate underneath of the North American plate, when you shove the Juan de Fuca plate under there, you're also going to get earthquakes. They could be shallow if they happen here. They could be deep if they happen here. But eventually, this plate is going to come in contact with enough of the asthenosphere, or the upper mantle, that it's going to melt. And this material was already less dense than the mantle to begin with. That's why it was the crust. Now it's going to seep through the earth and get back out in the form of a volcano. These volcanoes tend to be stratovolcanoes. I know some of you have not had a lesson on volcanoes yet. Some of you have. But they're stratovolcanoes. They're violent. They erupt big. Big explosions, lots of gas, lots of smoke, lots of thick lava coming out of there. So they're pretty volatile volcanoes once they finally do erupt. I'll show you quickly. This is the old oceanic and young oceanic. So you see the old oceanic crust is subducting beneath the young oceanic crust. In this convergent plate boundary, you're still going to get that melting. Now we're out in the middle of the ocean, so instead of getting volcanoes on land, you're going to get volcanoes in the ocean, and then those volcanoes, if they get to be big enough, can actually rise above the surface of the ocean and become islands. In this case here, they're pointing to the Aleutian island chain, which is in Alaska. And this chain of islands is all volcanic and is formed just by this. You got oceanic crust and oceanic crust subducting beneath themselves. There's a quick picture of what those islands look like. Clearly volcanoes. When you get to continental, it's kind of like a smashing contest where the mountains just push up. The author of the video here is using graham crackers, I think they are, or like a kid's granola bar, but he's demonstrating that if you take things of similar density and shove them into each other like this, you get a lot of folding and faulting as the mountains grow. So our tallest mountains on the planet are the Himalayas. He's showing that here. That's because the Indian plate is smashing into the Eurasian plate, and it's still smashing into it. It isn't like it's stopped. Now, a couple things I wanted to point out about convergent plate boundaries before we leave them behind. You get two phenomena here associated with all this just pushing together, this regional metamorphism. You're like, wait, metamorphism? I thought we were talking about plate boundaries. We are. You're pushing huge amounts of rock together, so you're going to get, in this case, I like the word strata more than layers, but you guys don't have to mess with that right now. I just want to show you what I'm talking about. One of the things they've been doing on the Regents a little more recently is like showing real photographs of outcrops, like rock outcrops like this, and they'll point to this and say, hey, what's going on here? Now, if you see folded rock like this, the rock folds because it is being pushed by plates. Rocks, these were horizontal sedimentary rock layers. They were pushed, and if they're given the time, they will realign themselves metamorphically, and they will fold into these rock layers. Now, the key is, this is metamorphic rock. Some of you may already know that just from looking at map symbols or remembering things about banding and stuff, but even on a large scale, these rocks here are metamorphic. So what they may ask on a question like this is they'll give you a picture like this. And the Regents might say, hey, what type of plate boundary caused this rock formation? Convergent. Like, wait, do I have to say continental, oceanic? Not really. Just stick with convergent. You'll probably be fine. And then they might say, great. Now, what type of rock is right here? And they'll point to one of these sections of rock, and they'll give you some choices. Whichever one's metamorphic, regional metamorphic, is probably going to be your answer. So these are metamorphic rocks in folded rock layers. They're really pretty. I like folded rocks myself, but they're going to be metamorphic rock in there, and they're caused by regional metamorphism, which is caused by huge giant earth plates smashing into each other, and the rock saying, I'm under an incredible amount of stress. I'm going to change and realign myself and go with this so that I can alleviate some of the stress. Now, if it cannot fold, because if it's given enough time, it will fold, but if it cannot fold quick enough, then it will break. And if it breaks, we don't call it folded, we call it faulted. So faulted rock trips students up a lot on the Regents. So here's a person standing next to a faulted rock layer. Like, wait, what do you mean? Well, you can see that this bluish area here was supposed to line up. From what we understand about sedimentary rocks and layers, this blue layer was deposited or formed the same time as this blue layer over here. But what's in the middle here? A big crack. So at some point, something was pushing on these rocks, and they couldn't compensate for that in enough time, or it happened too suddenly, and they broke and caused an earthquake. At some point in the past, when this broke, it caused an earthquake. But what's left here is what we call faulted rock. So what they'll do is they'll ask you to sometimes point to the fault, which in this case is right here. Or they will give you something like this. Here's the fault right here. You can see it's got the layers offset. In other words, they're not lined up anymore. And there is the fault. Let's see if I can, for region stuff, like they'll give you a picture like this. And I've seen this almost too many times where they give a faulted rock sequence like this. And they'll ask some questions like, hey, what is this? Oh, you look at your page 7 of your reference table. It's sandstone. Great. What's this? It's limestone. Perfect. What's this? And they point to the fault. And the kid doesn't know what to say. The student doesn't know what to say because they forgot, if they weren't listening, or that was just like a day when they were really into their Apple Watch. They just couldn't stop texting their friend about something that happened on Saturday. So they're like, I don't know. So what the students write is they write weird stuff like, well, not real weird, but they're going to write layers, or they're going to write disjointed, or they'll make up a word like broken. But this has a name in earth science. If it's a line going like that and it offsets the layers, we call it a fault, and you should call it a fault if they ask about what this thing is. So if they point to the line and they say, what is this? You should remark that it's faulting. If they give you a picture and they're like, what is this right here? Because this is a pretty, kind of a beautiful fault in my opinion. This is the fault right here. You can see that these layers belong together and they're no longer together, so we're going to go ahead and call that a fault. Okay. The divergent plate boundaries are kind of the crux for what we're really talking about today. This is going to be really confusing for people just to understand, but once you understand it, or at least I will say accept it, then it's not too hard. So this is the thing about divergent plate boundaries. Number one, a divergent plate boundary is where we have rocks that are, I'm sorry, one second, I was on the wrong thing. Okay, divergent plate boundary. This is where we have plates that are pulling apart, and when they do, they're going to release lava, and the lava we get out of these things here is going to be basalt, and we know that from the reference table because it said oceanic crust is basaltic. In other words, where this pulls apart, they're showing a continental one. Most of the ones we have here are actually these mid-ocean bridges. You'll see them all over your reference table. You have lava coming out in the form of basalt. Now, the thing about the basalt is a mafic rock. So there's pieces of iron in it, and what happens is the iron is going to, because it's metal, it's going to align themselves to wherever the North Pole is, the magnetic North Pole. So if you're a rock that's being formed, we can like freeze iron in there just by, it's like pointed to the North Pole, and that's where it stays because it's locked in the rock. And what we found out by looking back in time is that the Earth's magnetic pole has actually reversed several times in the Earth's past. So I want to be clear here. The pole has flipped over. The Earth's magnetic field has flipped over several times in the past. We don't really know what this looks like because it hasn't happened in any recent times. I mean, it could happen any day. Some people say it's actually due to happen soon, and that the magnetic pole of the Earth is actually getting weaker. So some scientists think that it's gearing up to flip, and when it does, we're not sure what that's exactly going to look like. But what we can say is we don't think we're going to die, because this has happened, I believe, a few times since mammals have been on the planet, and it doesn't correlate with mass extinction. So that's a good thing. But when these flip over, all of the little pieces of iron inside of the new forming rock will now point to the South Pole. And then when you get eruptions in the future, if it flips back, it's going to point to the North Pole. Now, I want to be really clear about something. The Earth is not flipping. The Earth's really heavy. If you flip the Earth over, that wobble or that flipping of the Earth would actually cause us to either careen into the sun or careen off into outer space. We'd either melt or freeze. We're not flipping the Earth over. It's just the magnetic, it's the magnetosphere, and it's the poles that are really, this is an outer core phenomenon. So here they're showing a volcano, and they're saying, hey, look, in the past we had reversed polarity. Now, reversed polarity means that the North Pole, our magnetic North Pole was down at the South Pole. Normal means our magnetic North Pole is where the North Pole is. They're saying it's flipped. If we look at these layers of the volcano, we can see that it's flipped. Now, what it also does is it shows up in the seafloor. They call this magnetic striping. So as this moves forward, you're going to see that as the plate pulls apart and new lava is coming, you're going to see a record of the magnetic North Pole flipping throughout time. And this is sometimes referred to as mirroring, because what's happening on one side of the ocean plate is happening on the other side. One question they like to give is they'll give you half of this, and they'll ask you to draw the other half with a scale. So you got to like measure how fat these stripes are and make them line up. So just a real quick recap. The normal polarity means that the iron in the rock is pointing to our North Pole, where it is, currently up to the top of the Earth, and if it's reversed, it's pointing to the South Pole. And as these pull apart, we get a record of flipped polarity, reversed polarity throughout time.